All right. Simmer down. It's hump day, Wednesday. So we're sort of getting toward the grab bag part of this class. So we talked about, three big operating system subsystems focused on multiplexing and creating abstractions for the CPU, for memory, and for the disk. That's done. So at this point, we're sort of going to move on. We'll talk a little bit about OS structure today, a little bit about performance on Friday, a little bit about virtualization, and then maybe if we run out of stuff, we might go back and do a couple of more lectures touching a little bit on earlier material. So maybe it'd be fun to go through a lecture on the x86 virtual memory system, if I can find a good one, since that's a hairy beast. And also maybe we'll look a little bit at file systems on flash devices, which are pretty interesting. But today we're going to talk about how operating systems are actually structured. And this gets us into this whole universe of different types of kernels, right? Microkernels, monolithic kernels, hybrid kernels, exokernels, multi-kernels. A lot of things, like of the universe of things that you could put in front of kernel, a lot of it has been explored. So we'll talk a little bit about what these designs mean and why you should care, right? What is there to be learned here about from the way these big complex systems are structured. All right, so thanks to Jinghao, who somehow managed to crank through, Jinghao and Zihei managed to crank through pretty much all the midterms in only a couple days, which I'm shocked by. Maybe they just gave you all full credit. Who knows? That's a fast way to grade. So we're going to start returning them either tomorrow or Friday. Once we get the grades entered, we'll have them available during office hours. I'm not going to hand them back during class, because that creates a big, ugly mob scene. But if you want your exam back, once we have it, you're welcome to come to office hours and pick it up. And we will have, maybe we'll turn them, we'll also have them available maybe after class on Friday. Right? So not during class, but we will have them outside class for you to pick up. On Monday, we'll spend a little bit of time talking about the midterm. Once I have some statistics put together. The statistics will also be embedded in the solution set in the way that we did in the past couple of years, right? So you should be able to go through the solution set, and see an overall breakdown of how you did, and then on a per question basis. If you want to come complain about a grade on a particular question, right? I mean, the course staff makes mistakes. Not many, but a couple. It's been known to happen, right? We have some existence proofs of this. So if you want to challenge a mark on a particular grade, the way to do that, so first of all, we're going to limit the total number of points that you can challenge per midterm, because we just don't want to rehash every grade on every question. And because, the laws of statistics indicate that our errors should be evenly distributed throughout all the exams, right? And it's very unlikely that we completely missed every brilliant thing you wrote on your exam from start to finish, right? It's unlikely. So the other thing, if you want to come in and talk to us about your grade, the way to do that is to get the solution set, look at the rubric. Oops, sorry. The rubric is what the course staff has used to assign points for each question. If you think that there's something wrong, you should come in and you should say, here's what I got based on the rubric, here's what I think I should have gotten, and here's why, right? We are not going to entertain sort of fishing expeditions of the type, I think I should have done better on this question than I did, right? And I don't know why, but why don't we talk about it together, right? We're not going to do that, right? So if you come to us with a very specific reason that you should have more points, then that means that the time that we spend together exploring whether or not you're right is time well spent, right? So please start, if you're not familiar with the rubric and you come ask a question, we're going to tell you, go look at the rubric and come back, okay? I'll let you guys see the exams first. Who knows? Maybe you'll all be happy with your grade. It's probably happened at least once in the history of the universe, yeah.
Are you going to post on Piazza whether picking them up starts tomorrow?
Yeah, I'll let you guys know as soon as they're ready to go. I mean, Jinghao told me that they're done. I just need to get the grades into our fancy grading system, namely a spreadsheet. Pretty sophisticated. All right, so assignment 3 at 4 weeks from tomorrow. The time will go fast. If you want to go it alone on this assignment, the deadline to ask us for that is tomorrow. If we don't receive your request tomorrow, you are working together, right? And you will not be split up later in the semester. And next week, now that after we give Zihei and Jinghao a few days to recover from what I'm sure was the incredibly pleasurable experience of reading all your answers, all your right answers to all the really interesting and fascinating midterm questions, they'll be back holding regular office hours next week. All right. Any questions about course administrivia? OK, I'm sure you guys will have some after you see your marks. All right, so today we're going to talk sort of about how to structure. So we've talked, and you guys probably are starting to develop some appreciation for this. Some of you guys probably addressed some of these design questions when you did assignment 2, and you will certainly have them when you do assignment 3, because assignment 3 is a much more complicated assignment to design and to build, because there's a lot of internal structure to what you're doing, and you're building a big sort of complicated, rather than an assignment 2, which is sort of a small piece of code connecting one interface to another interface. In most cases, assignment 3 is a very easily specified but large body of code that you get to write primarily all yourself, which is what's fun about it. And so up to this point, we've talked about scheduling, process management, memory management. What else? What other stuff do operating systems do that we haven't covered? Just to give you a sense of how this continues to get more complex. I mean, there's already quite a bit of functionality needed to do this relatively simple things we've talked about here, right? Provide these abstractions and multiplex these resources. But what else would you usually find in a modern kernel? Yeah.
Power management.
OK, yeah, there might be some energy or power management. That can be particularly complicated. Lots of devices do different things. This is why your laptop still won't go to sleep when you shut the lid, right? Unless you have a Mac, because then you only have 3 hardware devices to worry about, right? So it's easier to optimize. Yeah, Thomas.
So I guess I/O management.
OK, there's probably some stuff built into the I/O layer to allow you to do. We talked about this a little bit at the file system level, like quotas and stuff like that. But you guys are missing something big that you would be very sad if you did not have. Yeah. OK, so the drivers for different devices. Although there's a part of the system I think you would miss more than you would miss if you couldn't plug in your numeric keypad, like my mom wants to, because she knows how to do all that crazy numeric coding stuff that people don't do anymore. Yeah.
Network.
There we go. Yeah, like a network, the network stack, right? Which is pretty big. Not something we talk about in this class, mainly because there's a whole other course devoted to networking, but. There is a big, complicated piece of code that implements in the kernel that implements networking and the various drivers and higher level protocols that are required to do this, right? A lot of stuff about sort of user and job control, right? So just an implementation of users, assigning permissions, checking permissions when users try to do various things, and then the per user accounting that keeps track of how much of the machine is each user using. We talked about device drivers. Right? We'll come back to device drivers a little bit later today. That's certainly a huge part of operating systems, is figuring out how to connect all the cool things you buy at Best Buy to your computer. So things start to get kind of, is there more? No, that's it. There could be more, right? I mean, this was I think this was a simple diagram I found somewhere on the interweb. But there's a lot of different pieces of different functionality that operating systems have to provide, right? And modern operating systems are really, I mean, you guys, OS 161. How many of you guys would describe that in terms of the code you worked on as like a medium to large code base? Yeah, that's probably pretty accurate, right? That you should go look at Linux, right? Like OS 161 is a very tiny, stripped down, like simplified version of a real modern operating system. But if you take Ken Smith's class over the summer and actually do some real hacking on BSD, one of the things that's nice about OS 161 is it's structured in a way that should at least get you a little bit farther up the learning curve when you actually sit down with a real sort of modern operating system, right? It's doing all sorts of cool things that OS 161 doesn't do. I've already showed this. You guys remember, this is the scene from The Social Network with the crazy slide. Yeah, I already showed this. I knew I was going to show this at some point, so I won't show it again, but it's funny. So essentially, a lot of early kernel designs, on some level, remember the kernel exists to make the computer resources, including things that we think of as devices, but then also the CPU and memory and other kernel sort of hardware resources available to user programs. And monolithic kernels, it's kind of like, maybe I have an interface for my device drivers. I have the kernel interface, sort of the Unix system call interface that you guys have been implementing a little bit of. And then I just have this big blob of code, right? Monolithic, right? That runs in between and sort of does everything, right? And this is not an uncommon way of designing operating systems, right? There are some things about it that are somewhat appealing, right? But what this means, in a less sort of silly slide way, is that all the OS code is loaded into the same privileged address space, right? And the same shared address space, meaning that if you think about it, all the operating system code is sort of running as one big, extremely important, highly privileged program. What does that mean? You guys have, when we went back and we talked about earlier about processes and some of the barriers that operating systems put up around processes, what does it mean that, that your code and your partner's assignment 3 code are all running in one big sort of shared address space? What sort of unfortunate things can happen, Gino?
One small part of the kernel can break the whole kernel.
Yeah, so the fault anywhere can corrupt anything, right? So any part of the kernel code, any code that gets into this privileged shared address space can basically stomp on anything at once, right? Other memory, things that are in use by other threads within the kernel, which of course is heavily multi-threaded. It also means that all the operating system code is privileged, right? No user code is privileged, but all the OS code is privileged, right? So it all has privileged access to the machine, allowing it to do things like manipulate the virtual memory mapping so it can see any part of user memory. And also this means that there are these, some of the protection boundaries that we've talked about, some of the things that generate kernel faults, right? Or I should say that way, some things that happen in user space. So let's say a user space program, executes a divide by 0. That's sort of our favorite stupid program or problem in user space. What happens? What should happen? Yeah, Kevin. Yeah, the kernel just kills the process, right? What happens if a kernel throws the divide by 0 exception? It's kind of like the machine kills the kernel, right? And it's called a reboot. So this is a problem. And then the OS ends up, and it's just, this isn't, I'll make this blank, that's kind of funny, right? This isn't required, but it ends up, it kind of can happen, right? If you guys have ever built a big, so for example, how many people have built a big body of code from scratch? How many people have regretted the way they did that? Yeah, like the course website. Sorry, starting over this summer again for the 3rd time, right? Yeah, so a lot of times what we find is that as we design and implement these large software projects, we find that these decisions that we made early on that didn't seem very significant end up coming back to haunt us, and we don't like the way things work. But then as the project gets bigger, changing those things requires making more and more changes, and this can happen in operating systems as well, right? It's very, very difficult with a big modern operating system to do sort of a white sheet design, right? A clean slate design. You can't, right? There's too much to do, right? If you started over and tried to implement Linux from scratch, it would take you, 30 years, right? It's kind of how long it's taken. Actually, it'd probably take you longer, right? Unless you are the equivalent of thousands of people all over the world who are all pretty smart. You may be very smart, but you probably don't have that number of hours in the day. So this seems like a bad idea in general, right? And we'll talk a little bit about how this violates some of the good software design practices that you guys are taught as programmers, even now, right? Much less as you go off into the world and get better and better at doing this sort of thing. Why do operating systems end up being structured this way? Yeah, Adam.
Is it more performant because the kernel is active when it needs to be and you don't have
So yeah, so it can be more performant, right? Because you end up making the exchange, essentially if you write all of this in one big messy program, you place no limits on the type of interaction that can go on between two different parts of the kernel that might need to interact, right? What else, Doug?
It's simpler than having to divide the kernel up into different sections, because sometimes different parts of the kernel are used by the same thing, and then you have to find some way to make sure that different pieces of the kernel were communicating with each other properly.
Yeah, so I mean, and those are really the two reasons I wanted to get at, right? It's easy, right? It's, you know, when you're trying to build something, and this is an unfortunate tendency that we're trying to beat out of you in this class, right? It's easiest, and maybe some of you guys are pursuing this approach for assignment 3, right? I'll write the code first, and then the code will write the design, right?
Perfect.
Yeah, exactly, right? I'm optimizing, right? I'm going to parallelize the writing of the code and the design. Yeah, so this is easier to do, right? Yeah, until you hit the first of the thousands of bugs that you've caused yourself. And it's also, it is fast, right? Because the overhead of transitioning and moving data between modules in this kind of kernel, or you can think of the just different threads or different functions, is just function call overhead, right? So it's very fast. It doesn't require any sort of context switch into the kernel. It doesn't require, you know, restricting communication to patterns that are defined by particular interfaces. It's like anything goes, right? And because anything goes, right? So this is nice, right? But let's talk about some of the problems with this, right? I mean, you guys will probably already suspect that there are some issues. So I've broken this in 3 categories, right? One is rigidity, right? So the rhetorical question is, how is the monolithic kernel not like the Boy Scout motto? Probably people probably know the Boy Scout motto. What's the Boy Scout motto? Is that enough of a cultural reference that people will be able to get it? Yeah. Yeah, I think it's probably something grammatically tortured like that, but I always think of it as be prepared, right? Be always prepared. Be thou always prepared. So anyway, but the short version is be prepared, right? But what happens in a monolithic kernel if, again, you're out at Best Buy and you found this like really cool new like 3-part joystick that's going to allow you to finally, you know, master this racing game that you've been struggling with for weeks, and you plug it in, what happens? Yeah, it's just like, I don't know what to do, right? And early versions of these systems, sometimes it's pretty much what you know, this is not a joke. It pretty much was like, uh-oh, like I don't have a driver for that, and might not have the right libraries. So you need to launch the kernel configuration tool and check that box, and then wait like several days while I recompile myself from scratch, and then install that kernel and hope that you didn't mess up your existing configuration, and then you can play your game again, right? So it's not super awesome. How about this, right? So how is the monolithic kernel not, how is it like this cake? Can you guys read the cake? Don't read it aloud. Anyway, I mean, you guys know what this cake was trying to, now that I'm looking at this more carefully, there's several problems with this cake, right? Yeah, there's a bunch of, I mean, it's just sloppy, right? Like, I think this cake would make you sad even if it was spelled right, but it's not spelled right either, so maybe that was the best thing about it. So anyway, I mean, how are big monolithic kernels like this cake? What happens if your kernel just has like a small problem, right? Like a wee little bug somewhere, and yeah.
I was going to say change the entire kernel, or in this case, the
Yeah, yeah. So, you know, what this can cause is, you know, essentially, again, I mean, any bug anywhere in the kernel, we already talked about this, will crash the entire system, right? And that's not, and again, keep in mind that as kernels have evolved, they've gotten bigger and more complicated. We'll also talk about in a minute more and more of the code that runs inside the kernel. sadly isn't written by some of the really hardcore, awesome kernel developers, you know, who write binary with their 2 toes and like have been doing this since they were in the womb. Like, unfortunately, those guys don't write a lot of the code that runs in the kernel anymore. It's written by, you know, underpaid high school graduates who work at companies that make joysticks. And then finally, so there was this article once that I read about the amount of time that the military spends making PowerPoint presentations, which was really hilarious, actually. There are people apparently in the military whose entire job is to prepare PowerPoint slides, right? And here's the type of thing that they come up with, right? This was an actual slide from an actual presentation. I think this describes the relationship between different militant groups in Iraq or something. Anyway, it's not clear really how much information is being generated by this slide, other than this is complicated, right? And so what ends up happening is if you have to make small changes, right, like for example to correct a little bug, as kernels get more and more complicated, it becomes the amount you need to know to make a small change to a computer program, right? I mean, it generally grows as the size of the code base grows. That's sort of natural. But how fast it grows is a question, right? I would argue, you know, a well-written piece of code, maybe it grows linearly, maybe even a little bit slower than that. A badly written piece of code, it's like just exponential growth, right? The code base got twice as big. Now it's taking developers 4 times long to correct bugs, even once they find them, right? Because the code around the bug is so complicated. They didn't write it, has so many dependencies, they change one thing, and it causes 10 other things to break, right? Right, and these kernels, again, can get to the point where it's very difficult for other people to understand them. This is particularly challenging for, if you think about it, for big projects like Linux, right? Because Linux has a stable core group, a relatively stable core group of developers, but it also has benefited from the contributions of a lot of other people over the years who have had to be able to sit down and figure it out, right? So, you know, it's one thing to be like, oh, all this code is super awesome, and like, yeah, I get it. You know, I wrote the whole memory manager from scratch one night, you know, and then went, you know, and even had time to watch Seinfeld, 11. But these, you know, bringing new people into these software projects also means that you want to keep this under control, right? So let's talk about these 3 issues. So it's rigidity, safety, and complexity. And these are not the only problems with monolithic kernels, but the ones we'll talk about today because there's some interesting aspects of kernel design that have focused on solving these, and these have also given birth to some other types of kernel designs, right? All right, so when we talk about rigidity, we can talk about a lot of different problems, right? One is the inability to adapt to changes in hardware, difficulties in modifying how the kernel behaves, fixing bugs on the fly, and also, to some degree, rigidity also can reflect rigidity in the way that the operating system makes decisions that affect applications, right? What's an example of a decision that affects application performance that we've talked about in this class? The operating systems we've talked about, and you guys are working on building, don't provide applications any flexibility in making. Just one example, yeah. Meaning what? Well, but operating systems, I would argue operating systems have priorities that are designed to reflect this, right? But what's a policy decision that operating systems don't allow applications to help them make? I've got one in mind. There's probably a couple. Yeah?
Physical and user address translation?
Well, OK, we're getting warmer. What about that process, Adam? So there's some parts of scheduling, sure, yeah. I mean, you know, priorities could be this coarse grain control, right? On the other hand, you know, I can call thread yield. That's a way. I can't always, you know, necessarily express every scheduling pattern to the kernel. What about page replacement, right? The kernel is throwing pages out of my address space behind my back, which is cool, right? But hey, maybe I would like some little bit of say about which pages got trimmed, right? Wouldn't it be nice if the kernel could come to me and be like, look, I'm taking your pages, all right? I'm taking 10 pages. You get to pick the unlucky pages that are moving out to disk, right? It's not how it works, right? How it works is the kernel is sort of watching the application, trying to make these decisions by itself, right? And so there's an example there of maybe, if there was a safe way to ask applications to participate, they could help, right? So one way that a lot of systems have designed around this problem is through what are called loadable kernel modules. What loadable modules are is a way to load code dynamically into the kernel at runtime, right? And this solves another problem too, right? Which is that if you've, so has anyone here actually ever configured and built Linux for a machine? Yeah, I know which hands are going up. So you guys should try this sometime, just for fun, right? You don't even have to build it. Just try going through the kernel configuration scripts for Linux, right? This process can take hours, right? I'm serious, because the number of options that have emerged because of all the diversity in hardware and all the different features is incredible. And you'll read these things and you'll be like, I have no idea what that means, right? And sometimes that thing will be something that if you don't enable it, the machine won't boot, right? Which is sad. So thank God for Ubuntu, because no one has to do this anymore. But it also, so if you think about, the kernel as this big blob of code, right? These old monolithic kernels. Another consequence of this was that the kernel had to contain all the code for anything that might happen, right? If that code wasn't in the kernel when you booted, in the kernel image, then you couldn't mount that file system, for example, because the kernel would say, I don't know how to mount that file system, and you were stuck, right? So what this meant is that it's one thing to be prepared, right? It's another thing to be over-prepared, right? To the point where your kernel's gotten massive because you've prepared for every variety of 3- and 4-button mouse that could potentially ever be plugged into you, right? And so rather than doing this, what we can do is allow the kernel to load and unload functionality at runtime. So loadable modules are usually compiled alongside a specific version of the kernel. They can be independently recompiled. So if a developer fixes something, they can push out a new version of that module. It doesn't affect anything else. They're stored on disk until they're needed. And when they're needed, the kernel can open the module, load the code into the privileged address space, and allow the code to execute and do whatever it needs to do, right? These sound a lot like device drivers. And you can use these to support devices. But they can also support other types of kernel features, right? One example is file systems. So a lot of kernels don't compile very many file systems directly into the kernel image, but they'll include support for a lot of different file systems as loadable modules. So when you try to mount a file system, the kernel will figure out, OK, this is an ext2 file system. Good, because I've got an ext2 file system module lying around. I'm going to load that in, and then I'll allow it to support the file system that you're trying to mount, right? So these are more than just supporting device drivers. And I always hate to be categorical, because there's probably some exception out there, right? But most modern operating systems support some form of this behavior, right? Because it's a very, very useful idea. All right, so now let's talk about safety. Users tend to not like crashes, right? I mean, how many people like when their computer crashes? How many people's computer crashes on a regular basis? Really? Sorry. Is it VirtualBox? Anyway, no comment. And kernels don't want to crash too. And the thing that's really interesting about this, right? Think about, just perform the thought experiment. So all of like the really, really hot paths in the kernel, page allocation, scheduling, all of that stuff, think about who writes that, right? Who writes that code? And then think about things like, how often does that code get executed, right? And how many times a day are people essentially implicitly testing those code paths by executing them over and over and over again, right? And then you start to think about, is that where the bugs are in my kernel? No, right? That sort of stuff is solid, right? I mean, so where do these things come from, right? These things keep happening. I mean, look, I worked briefly at Microsoft, and there was one guy there who was in charge of the virtual memory subsystem of Windows, right? One dude. And I remember being in the meeting, and people were just sort of like talking about, oh, they were considering some change to something or another. And this guy walked in, and he was like, no. And then they just stopped talking about it. And he left like 2 minutes later, right? He was like, that's not going to happen, bye, right? And so he really like, and I was like, oh, okay. Well, I guess we should talk about something else. Yeah, so where do these problems come from? Does anyone know? Everyone knows this by now. Windows has done a good job. Yeah, 89%. This is probably an old thing. It's probably, I don't know what it is for Vista or some of the later versions, right? But 90% of the XP crashes are caused by device drivers, right? But if you guys have parents who use computers, when this happens, who do they call? If they can call, or send flame emails to, or I don't know, hate mail, or whatever they do, right? They send it to Windows, to Microsoft, right? Oh, Microsoft crashed again, you know? Windows makes this crappy product, you know? So, and this has been a problem. This is, you know, Microsoft's very defensive about this. At least they were 10 years ago, right? And it's unfortunate, right? Because they get tagged for all of these crashes, right? And then it's like, well, maybe you shouldn't have plugged in the mouse from, you know, Sketchy Core, right? You know, the 10-year-old mouse that you bought that like says it's actually only supported up through Windows like 3.1 or something, right? I mean, maybe that wasn't a great thing to plug into your computer, right? So this is a problem, but you know, so this isn't a problem that kernels have created, but it's a problem that they've been sort of forced to solve, right? This is also funny. I don't know how many of you guys know this, but they've done studies of device driver lineage, right? So essentially, a lot of companies, as they push out newer versions of products, what they do, or what the, you know, again, what the new graduate who has to write the driver does, right? What do you think they do? They start with the old driver, right? So for, you know, SuperMouse 4.0, they start with the driver for SuperMouse 3.9, right? And then they add like the new SuperMouse features. So, you know, so what happens when there are bugs in SuperMouse 3.2 that don't get detected for a couple of years or a couple of months? By this point, SuperMouse 5.0 is out, right? They just percolate downstream, right? And so they've done these studies where they find one bug, and then they can show that every downstream driver, right, is also affected by the same problem. Right? And so this is just sort of, I thought, a funny observation. Yeah, exactly. But most of us are forced to do this, sadly, right? I mean, it's not that simple. But you know, in general, it would be better if you didn't use code that you didn't understand. Yeah.
Is that a bad thing? You gotta kind of wonder, because then if you're still working on the same code base and you're fixing these bugs in all these different mouses,
yeah.
I mean, yeah, the bugs are getting carried on.
No, yeah, that's a good point. I'm not sure it is a bad thing. I think that's a good point, right? I mean, better to have a common, yeah, there'd probably be more bugs if everyone started from scratch, right? They would just be new bugs, right? Rather than old ones, right? But yeah, I think it's so yeah, I'm not trying to claim this is a bad thing necessarily, right? But it certainly is an interesting thing, at least to me. All right, so because of this real practical problem that affects a lot of computer systems, there's been a lot of work on device driver safety. Restricted languages, better interfaces, trying to write libraries to help device driver writers, trying to test device drivers, trying to run device drivers in unprivileged mode so they actually can't crash the entire system. Automatic synthesis of device drivers was hot a couple years ago. You know, where I can essentially take a device specification and have a tool that will automatically generate code for a device driver from it, which is pretty awesome and is going to put tens of thousands of junior programmers out of work. It's kind of sad. Or at least being able to verify them, right? Can I do safety tests? And Microsoft has driven a lot of this development. Or I think one thing that they've started to do is actually try to apply virtualization technologies, right? So can I run the device driver in essentially what's a virtualized environment with the similar protection properties, right? And most of these approaches take this, in most of these tools essentially assume that device drivers are going to be buggy and simply try to make sure that the bug will only cause that device to stop working and not crash your entire computer, right? So the and so there's an interesting observation baked into this, right? Which is that the problem here is that these device drivers, on some level, they need low-level access to hardware. Why? Why do they need low-level access to hardware? Why would a device driver need low-level access to a device? Because it's a device driver. Duh. But maybe, another route to approaching this problem, right, is to, rather than relying on hardware, right, let's try to use different languages, right? Let's try to get support for solving this problem from the language level, right? And what a lot of people have started to do, so I think it's really fascinating, right? I mean, I think that you guys will live to see this change, right? Maybe you won't care in 10 years, right? Or 20 years, or 30 years. It's getting less and less likely as the time goes on, obviously. But I think you guys will probably live to see the widespread deployment of operating system kernels written in let's just put it this way, languages other than C, right? Managed languages, right? Languages that don't force you to do explicit memory allocation. Languages that are more like Java than C, right? Not Java, no. Please, no. So, but, something that's not C, right? I think that computers have gotten fast enough, and some of the safety problems that we're dealing with have gotten difficult enough that this will probably happen, right? Yeah, so now, the fun thing is this whole garbage collection problem, which sounds like this academic issue, is now really, I mean, it's not academic, it's always a performance problem, but now it's like an important performance problem. So now let's talk about complexity, right? So we talked about safety, we talked about rigidity. And now let's say, and I don't know, maybe I'm being optimistic about what a normal programmer would do, right? Let's say a good programmer, right? Someone who's taken Mike Buckley's software development class and has learned all these now software engineering principles. How do you structure a big development project? What's the natural thing to do? What's the best tool to combat sprawl and complexity in software projects? Yeah, Gina. Yeah, break it up into modules or small little pieces of code. I met this guy at a party around here who told me that he had not written a comment in a piece of code in like 10 years, right? He was proud. He was actually really proud of this, right? And he was like, well, no, it's just like, because what I do is I break all my code down into functions that are never more than 5 lines long, right? And he's like, and the idea is that the code should document itself, right? I started to do this too, but it's just completely out of laziness. It has nothing to do with it. I just got tired of writing comments, so I stopped. But anyway, we break it into modules, and then you establish interfaces between the modules. All this, we talked about interfaces a while ago in the types of the ways that interfaces lead to good design, right? And in the case of the operating system's kernel, there's this other interesting design requirement, which is we might want to minimize the amount of code that absolutely has to work properly and the amount of code that runs with kernel privilege, right? So if you imagine taking an operating system, breaking it up into these nice modules, building really good interfaces between the modules, but then you have this other design constraint, which is that the module that actually has to run with kernel privilege, if we can make that thing as small as possible and as limited as possible, then I have a very small piece of code that I have to check and test and really get right? And the rest of it, can kind of depend on that. So this is sort of accurately, there was a whole movement to design operating systems this way it's called and these were called microkernels, right? Microkernels didn't provide less, yeah, you could think of a microkernel, right? It's like one instruction, right? That's my microkernel. It doesn't do much, right? No, they provided all the features of bigger kernels. The idea was that, however, that rather than a typical kernel where you have all these kernel subsystems that run in kernel mode, right, in privileged mode, what I do is I reduce the stuff that runs in kernel mode into as little as I can, right? The things that I just have to do that can't be done on any other way. Usually that consisted of some scheduling, doing some virtual memory mapping, since that requires manipulating hardware, and then IPC. Right? We'll talk about why IPC, or inter-process communication, was so important to microkernels. And then everything else gets thrown out of kernel mode and is forced to run as kind of a user-level service, right? So my file systems no longer run in kernel mode, right? The kernel has to provide some sort of block interface to the file systems and make sure that they're not using other blocks that are allocated to other file systems. But other than that, my file systems run as unprivileged user processes, right? So this is nice. I can also write networking stacks, right? To some degree, I can provide support for address spaces, because it turns out that abstraction doesn't necessarily require being coupled to virtual memory translation if the translation is done by the kernel, right? And these user-level services now essentially communicate with each other when they need to, and in many cases they do need to, over using messages, right? And in theory, now this was always questionable, these user-level services providing stuff like the file system can crash, right? And just be restarted. So your file system has a bug in it. Somehow you've got it down that code path, it crashes, and then the machine keeps running. You certainly can't use that file system for a minute. And it's almost like you reboot your file system server, and life goes on, right? And this was, microkernels were a big hit, right, back in the 80s and 90s. There was a lot of work on this, right? And the problem was always performance. Right? Microkernel problem was always performance. And the reason is because, we talked about it earlier with monolithic kernels. The monolithic kernel permits the widest and fastest range of communication between kernel components that you can't, right? They're all running in the same address space. It's just a function call, right? Now, for example, when my file system wants to load data into the buffer cache, it has to send a message to the virtual memory server over IPC, right? That message needs to get sent into the kernel. That's one kernel message, sort of kernel boundary crossing. Then the kernel has to send that message over to the virtual memory subsystem. That's another boundary crossing, right? And it turns out that there's a fair amount of communication that you need to implement these servers in user space. And there were two common ways to improve microkernel performance. So this debate raged on for probably a decade, right? Where people would say, there's this microkernel design, this is awesome, and another group would say, it's terrible, it's really slow, right? And then the first group would say, well, we made it faster, it was just badly designed. And the second group would say, it's still really slow, right? And there were two ways to do this, right? So one way was, unfortunately, you could let stuff from user space sort of fall back into the kernel, right? So it was like, uh-oh, like conceptually that was awesome to run that in user space, and it was possible. It's possible to do correctly, given the microkernel architecture, but the performance is terrible. So back into the kernel it goes, right? So this is not really that ideal. And then what other people did, which was even more awesome / terrible, was they were like, what we really need to do is just implement the microkernel in assembly language, right? Because then it'll be super fast. And unfortunately, it also quickly becomes completely unmaintainable and extremely tied to the particular architecture of a given device. Now, these guys argued that that was OK, right? I mean, monolithic kernels have a certain amount of them that's written in assembly language. You guys have seen this in your OS 161 code. That's not completely weird. The problem is that, again, that stuff starts to get very device specific, right? So now I need to have a separate hand-tuned microkernel for every device architecture. And that's probably not going to happen, right? Yeah, Paul.
Do you need users running to use it? Or so every process has its own file system users running?
So processes in order to use a file system don't communicate with the kernel directly. They communicate with the kernel file server, right? So yeah. So the calls that would normally go into the kernel to access files now need to get routed to this other server, right? So a lot of the functionality is the same. What's different is that that code is not running with kernel privilege, right? And when it needs to run with kernel privilege, it has to communicate with the microkernel to do those things, right? It's a good question. So you know, to some degree, I mean, there are some microkernels left. I'll talk about one in a minute. But this was one of these really fun debates within the OS community that ended up benefiting everyone, right? So one of the things that microkernels did is that they gave us really, really fast IPC, right? That's the other thing that people did to make microkernels fast. They optimized the heck out of IPC, right? And so these really fast IPC mechanisms that were quite clever, and that benefits everybody because other things use IPC, right? A couple years ago, so one other route to safety that we didn't talk about is actually use static analysis techniques to formally verify your entire kernel, right? So I have a program now that can prove that my kernel is correct, right? The last person who thought he could do that was Dijkstra, right, in like 1950. A couple years ago, this team from Australia announced that they were actually able to formally verify a small microkernel operating system that they had built, right? So they essentially had a partial proof that this operating system was correct and would not crash. This would never have been possible on a monolithic kernel, right? There was just no way. And so to some degree, microkernels have allowed this to happen too, which is cool. Yeah, I already said it. OK. I don't want to talk about hybrid kernels. It's not that interesting. Yeah, hybrid kernels, right? So yeah. Hybrid kernels are essentially a monolithic kernel with better interfaces, right? So yeah, exactly, right? So we try to keep things conceptually clean inside our big blob of monolithic code. Again, not a bad idea, right? And Linus doesn't like this term. It's just marketing. So exokernels are another one of my favorite kernel designs because, and this actually motivated, at least for me, a lot of the conceptual way that I think about operating systems. These were developed at MIT in, oh man, in the late 90s, I think. And what they did is they said, look, operating systems should not implement abstractions. They should only multiplex system resources and let everything else happen above them. And this was a division of operating system responsibilities. It was very different than what other people had been able to implement, right? So again, they don't implement any abstractions, even messaging. All they do is verify and enforce all they do is multiplex resources, right? So for example, they will hand out memory to other parts of the system and enforce that those parts are only using the memory they're allowed to use, right? They do not implement address spaces, right? Address spaces are an abstraction. The abstraction requires multiplexing, but doesn't need to be done by the kernel, right? And this was quite a cool design. So the multi-kernel, it's like alphabet soup at this point. Multi-kernels are even more modern operating system design that essentially has started to say, look, we've done all this cool work on distributed systems, right? Some of you are taking, Steve's class or took Murat's class, have studied some of this stuff. But what's actually going on inside your computer now looks like a small distributed system. You've got multiple cores. So those cores are getting farther away from each other sometimes, meaning that it's actually difficult to transfer data between them. You see machines that don't have shared memory that's accessible to every core. And then you have all these other cores that are popping up. Someone did this count. I can't remember what it was. It was like iPhone 5 had like 20 different processors on it, right? Like maybe 2 of those are CPUs, like general purpose processors. Everything else is like for doing video decoding and supporting other very specialized parts of the system. So what the multi-kernel said is, let's acknowledge that there's this distributed system in the machine, and let's build an operating system that relies on some of these distributed systems principles to make this work, right? So we're coming back to this who cares question, right? Like why do we? I don't know. I hope maybe you should care because you just sat here and listened to me talk about it for an hour. So that's good enough reason to care. But I think just when you look at the overall big picture of operating system structure, I think there's a lot to learn here, right? I mean, these are pieces of code that are 60, 70 years old. And these design decisions and these arguments about how these systems should be built have played out in some really interesting ways over time. And they still are, right? I mean, I don't think we've seen the last of how these systems are going to be built. And the last thing, though, is that there's one big caveat about how to, for your own programming career, how to sort of incorporate some of these lessons, which is that if it doesn't, like, the thing about kernels is they have to be fast, right? And performance has trumped safety every time. For the code that you guys write, right? This is one of our systems design principles, right? Keep it simple, stupid, right? Don't over-design stuff. Break stuff down into modules. Implement a simple version of something first, and then you can optimize as you go, right? I'm not going to talk about interfaces, although that was And on Friday, we'll talk about benchmarking systems and performance, and we'll actually talk about sort of closing the loop here, which is that how do you identify the parts of your code that are causing performance problems and improve those parts and not other things? So we'll talk about that on Friday.